Thank you for coming. My name is Bill Zhang. I'm today a host, and I'm the product manager at Cloudera, responsible for Iceberg and the CDP Cloudera data platform integration. So today's topic is actually, we're going to focus on Iceberg. So we're talking about breaking the ice around the Apache Iceberg to drive next generation analytics. So we have several speakers here. So Aman Sinha, myself, Asif, all from Cloudera. We also have two distinguished engineers from LinkedIn, also going to talk about their focus on the Iceberg. So just today's agenda, right? So we already gone through, this is the kind of snacks and drinks you guys can enjoy. Around 5:45, pizza will be delivered. So we have three main topics. One is that Aman Sinha is going to talk about Hive Impala integration with Iceberg. So Aman is going to do a materialized view on top of Iceberg demo, and I'm going to do a couple of demos to showcase the in-place partition evolution as well as time travel. Asif is going to talk about some of the performance improvement that when we integrating Spark engine with Iceberg as well. And lastly, that LinkedIn and folks will actually present the incremental view maintenance with Iceberg. So without further ado, Aman, please.
Thanks, Bill. So let's move on to the next part of the agenda. My name is Aman Sinha. I work in the Cloudera data warehouse group here, and I work on Hive and Impala query engines specifically. I also manage teams which work on the optimizer metadata pieces of these engines. So today I'm going to talk about Hive and Impala integration with Iceberg. So let's start with an intro slide. We have an ongoing journey with Cloudera and Iceberg integration. So currently, as many people might know, Cloudera manages close to a zettabyte or more of data on-prem and cloud. And the expectation is that in 3 years, we will be moving all of this data over to Iceberg format. So that's a pretty big commitment that we want to move forward with, Iceberg as a table format unified across both on-prem as well as cloud. We also are very committed to doing community engagements and contributions. So very recently we have contributed certain PRs to the Iceberg open source, in particular the manifest caching to speed up query compilation. We also work on the TPCDS benchmarking and performance evaluation, and try to share, even including in this talk, we will also share some learnings from doing performance evaluation on large data sets in TPCDS, and doing various types of concurrency and other types of workloads. The core part of the talk is about integrating Hive and Impala with Iceberg. So across different engines within Cloudera, we are integrating with Iceberg, Hive, Impala, NiFi, and then also we are our Spark and Flink engines are also doing a lot of work around Iceberg. And we are standardizing on the Metastore, Hive Metastore for all compute engines. Of course, there is also metadata stored in Iceberg. Especially, we are also leveraging the Puffin statistics stored in the Puffin file format in Iceberg. So I'll touch a little bit about that in the rest of the talk. All the code and docs are available upstream. We also do these kind of evangelization for promoting what our open source commitment is in these types of meetups. And of course, blogs and demos. So this is just to show the overall architecture. As you can see on the base, we have on the base layer, we have all the core platform, the storage layer.
So did you speak at the Chennai one? Did you speak at the Chennai one, or you just kind of heard about it? Shiv was. Shiv, that's right. Shiv was. That's right. She did say Shiv was in town.
Can you please mute yourself, whoever is speaking?
To get some insights.
Yeah.
Why are they here?
Yeah.
That's why building us like please.
Yeah.
Whoever is speaking on the phone on the call, please mute yourself.
Hey, Wendy, you need to go on mute.
I saw you sent it. I've been running back.
Hey, Wendy, your phone call is on broadcast.
Okay, I think we are past that. As I was saying, we at the base layer we want to create this platform which is based on the Iceberg table format, right? And this forms the unified data layer. And on the top we have different types of multifunctional analytic engines, which each of them can have their own strengths. Flink, Spark, Impala, Hive, all of these would have their own strengths and weaknesses, and we want to enable all of them to be able to access the tables in Iceberg format. And in the middle, we also provide data governance and management through Ranger, Atlas types of products in the middle. So this is a fairly sort of unified view of the whole architecture. Okay, transitioning to the actual query engines. So I'll start with Hive. And since the last meetup, we have actually worked quite a bit on enhancements, especially around the V2 support. Iceberg V2, as you know, allows row level deletes. And so we now support the CRUD operations merge and read, or V2. We also support the CTAS create table like statements, time travel queries. Also, there was some support added for setting the current snapshot ID. Hive also supports reading and writing in all of these different file formats, ORC, RK, Avro. There's also work done to improve the performance for V2 tables. So vectorization was supported on other types of table formats previously, but not on Iceberg. And now we also support that for Iceberg tables. There is also support for schema evolution. As you know, Iceberg allows schema evolution where you can rename columns, you can add drop columns. How do we handle that within Hive? This is speaking to that. We also did other performance improvements. And then we also added Ranger support for Hive Iceberg tables. So some of these have their open source Jira IDs also listed in the parentheses in case we don't, since I won't have time to dive into each of them, but you can take a look at it if you're interested. So the first item is about the incremental rebuild of materialized views. And I'll do a little demo around that in a few minutes. The second one is about the vectorization fixes for update delete merges. And as I mentioned in the beginning, we are also working on integrating with the Puffin file format in Iceberg. So Iceberg allows storing the statistics, column level statistics, table level statistics in a standard format called Puffin. And so what we have done is that if you collect these statistics in Hive, we will store them in this Puffin file format and use it from there. Optimize deletes. So deletes are very unique to V2, right? So if you do deletes in Iceberg, it creates positional delete files, in the file system. So how do you take advantage? How do you handle those positional delete files, right? So if you can imagine, it's not a very simple or very performant operation unless you do some performance improvements there, because you have to read the base data and you have to read the positional delete files. So we have done some work around to optimize that type of reading. One of the key aspects of that is basically using a bitmap index to represent the positional deletes. So we create those bitmap indexes, and that allows us to sort of seek to the appropriate record in the data files that have been deleted. The rename table support was added. And then the other big one is migration of external tables to Iceberg tables, right? So this is a key piece of, allowing customers and users to do simple migration, right? They don't want to go through a very expensive process. So there is syntax and semantic support added to do migration using just, something simple like alter table, change the table properties of the current table to an Iceberg table format. And the Jira mentioned there describes things in more detail. We have also done some work around caching of the manifest files. So some people might be aware that Iceberg, provides this flexibility of doing schema evolution, partition evolution, but it comes at the cost of also, having these different manifest files. So when we did some experiments with, TPCDS and others, we found that the query planning time is affected because of the fact that we were fetching the manifest files from, let's say in this case, S3 or Azure, and we were doing a lot of repeated seeks for these manifest files from the cloud storage. So caching of the manifest files is very important for Hive as well as for Impala, as we will see later. Some items that are in progress, loading data via temp table. So this is one of those things where, if you have, let's say you have a bunch of files, text files, Parquet files sitting in some location on S3, you want to create an Iceberg table out of that. How do you go about doing that? And these are not real tables. They're just data sitting in some folder. So in this work, basically it was what we did was we read these files into actually a temporary table, and then we convert it to an Iceberg table. And there's some reasons for that, because Iceberg expects that each column is identified by a field ID. So in order to do that, you have to actually convert it into some kind of intermediate format to get to that field ID, because you can basically Iceberg tracks different columns based on positional indexes within the table. The next one was the delete position index and caching support to speed up delete processing. So I talked about using the bitmap index for doing this kind of performant reads of delete files. And then the column stats are stored in some type of cached storage here. So just jumping to the materialized view part. So a key contribution that we made recently was to allow creating materialized view in Iceberg table format, backed by ORC or Parquet, right? So you have Iceberg tables, you want to create materialized views, which can be partitioned also, and they can be partitioned on different keys compared to the base tables. And then what do you do after that? So you can do query rewrites based on the materialized views. But let's say your base data is changing. You want the materialized views to be maintained. And we can do that maintenance either through a full rebuild, or we can do it through an incremental rebuild process. And I'll do a quick demo about that. And we are basically maintaining the mapping of the snapshots in the base table, from the base table, to see which snapshot was the materialized view created from. So let's say you have 3-table join. Each of those tables that contributes to the materialized view, we will maintain those snapshots in our internal metadata. And then we will figure out, okay, if some new data was added, some snapshot changed, now we have to update the materialized view. We are also, while I'm talking about materialized views, I do want to mention that Iceberg community has a proposal, has a specification rather, for materialized views. And so we are looking into how we can take our existing materialized view metadata and then map it to the Iceberg materialized view metadata. Okay, so for the demo, I'll do a short demo on TPCDS on a 1 GB scale factor, where I'm joining 3 tables and doing some group by and aggregation. And then I'm going to show what happens when we insert data into the base table. So let me just switch to a terminal. Okay, so I have here a Hive session, and I'm going to just go to a database which has a few tables. It has customer, date dim, and store sales tables. Store sales. So store sales is the sort of fact table in TPCDS. So if I do a describe, here you can see that it is a Iceberg table, and it has currently 2.7 million rows spread across 1825 files. It has, it is partitioned on some key. And similarly, the other tables are also Iceberg tables. So I'm going to create a materialized view. And this view is simply doing a sort of year total based on the country and the year. So let's go ahead and do that. So this is the initial creation of the materialized view. It's basically reading the data from those base tables, doing the joins, grouping and aggregations. So the first part takes a few seconds, few tenths of seconds, and then I'm going to do a describe. Okay, as you can see here, 848 rows came into the materialized view. So this is the number of rows currently present in the materialized view. The original tables were few million rows joined with some hundreds of thousands of rows. And I'm going to do a describe of this. So this is a materialized view which which is an Iceberg format. And it has the key, there are different attributes of this, but the main thing is that, okay, it's enabled for rewrites. It has some, it has the view definition here, and so on. Now let's do a quick explain of the, doing a query which is kind of a subset of the original query. You can see that this explain command shows that the materialized view was used. Now let's go ahead and insert some rows in the base table. Okay, so now you can see that we have, in Iceberg, basically a new snapshot would be created for, at this point, since a bunch of rows were inserted, this snapshots sort of metadata table in Iceberg allows you to look at, the state of the current, details about the current snapshot. So this is the snapshot ID and so on. Now let's look at the base. Let's look at the materialized view again. And at this point, you would expect that since the data has changed, the materialized view would be obsolete, and you can see that it is outdated for rewriting. Now let's do a rebuild of the materialized view. So currently this process is a manual process. You do have to trigger the rebuild, but in the future we plan to automate that through different mechanisms. So there are different approaches to doing that. So here's the explain plan, and the key part, you don't have to worry about the rest of it, but the key part of it is, let's look at this table, right? The main table, the store sales table. We have this predicate or some type of, you can call it like as of reading, the Iceberg table. So we want to only get the delta changes starting from this version. So this predicate is specific to Iceberg. And then it'll read those delta changes and apply it to the overall materialized view, and then compute the final output. So let's run the rebuild. This will also take a few seconds, but the expectation is that this should run faster than rebuilding the whole materialized view. So in the beginning, when we created the materialized view, it took about 20 plus seconds. And now, because it is delta changes, it takes shorter time. So that's basically concludes that part of the demo. Yeah, that's a good question. So that if you look at the materialized view definition, it was doing a group by on 2 columns. So the rows that were inserted, after you do the grouping, it collapses to 2 columns. Yeah, I mean 2 rows rather, 2 rows, not 2 columns.
Aman, can you please repeat the question for people on the Zoom?
Okay. The question was in the script, basically we were inserting 5 rows, right? And then in the actual output here, it was showing 2 rows affected. So why is that? And the answer is yes. The original those 5 rows, once you group them on the grouping keys, then it comes down to 2 rows.
Okay, thanks.
Okay, so let's move on to Impala. Impala also has done a bunch of work around Iceberg integration. So I'm again, in this case, I'm not going to go through the full list, but sort of highlight a few important ones. The first one is around the optimize count star query. So if you have the if you're doing ingestion, if you're doing any writes into the table, the idea is that the count queries can be satisfied by just the statistics. So if you're not doing so let's take the simple case where you're only inserting rows into the Iceberg table, then the count star query can go and fetch the updated table count and return the results very quickly. So you don't have to do the aggregation. The second one is about the cardinality estimation improvement for Iceberg table with position delete. So there was some area where we found that when you're doing deletes operations, so when we delete, let's say 10 rows in the table, Impala would be doing a anti-join of the original base data with the deleted files. So when we do the anti-join, the plan was sort of doubling the cardinality, thinking that both of the both sides were the size of the base table, and that was incorrect. So that was more of a sort of a bug fix. In terms of overall predicate push down, right? So conceptually, think of you're given a complex query and you're querying querying Iceberg table. Iceberg provides very good support. The library provides very good support for push down of filters on the partitioning key, right? So you can have a complex set of predicates in your query, some of which are partitioning keys, some are not. So the the engine will split it up and only push the necessary things to Iceberg and do the partition pruning, and then apply the rest of the predicates within Impala. So as part of this, as I had mentioned earlier about the caching of the manifest file. So Impala has added this capability to both the coordinator as well as the catalog daemon. Rollback support was added. Then there's this load data in path, which is similar to the other feature I described in Hive, where you have a set of files and you want to load them into an Iceberg table. As far as V2 enhancements are concerned, so we added V2 read support in Impala. And then in the future, we will also provide the write support for that. Another big piece is the Iceberg metadata query support, right? So Iceberg exposes the metadata through some types of system. You can query the metadata from the Iceberg tables, like I was showing for snapshots. The output that I showed. Then there's also things around partitions. Currently, you can do something like select star from the table.partitions, and Iceberg will return all the partition information. But this just provides a better interface to query the metadata. the reading the equality deletes, this is another optimization for Impala. And that is work in progress. Delete and update is in the pipeline. It's in progress. Binary data type support, and then finally the migrate table support, similar to what Hive does. So one of the things that we have experienced during performance evaluation of Iceberg is the well-known merge on read versus copy on write trade-off, right? So Iceberg, because of the fact that you have these delta files, how do you handle that? Do you handle it at the time of the data ingestion, or do you handle it at the time of reading, doing the queries? So as you can imagine, there are trade-offs, right? So if your rate of change in the table is small, then you're better off doing the merge on read. If you have lots of, let's say you have more than 50% of the data is getting updated in the table, then you don't want to pay the price of at the time of read, reading all these delta files and then combining them with the original base table. So you ideally want those to be taken care of at the time of the write operation itself. So these are the sort of trade-offs that one has to worry about. And it will depend on, if you have a use case where you don't know exactly which way is the right way, you have to look at all the different percentage of read and write operations that are going on. So the other parts of these are, just what are the recommended tunable parameters. So we did some tuning for instance, for Hive, in order to handle large manifest files. We can tune certain parameters for increasing the parallelism and doing those reads. So these are some recommended attributes. The next part is also again about improving the overall performance. So first one is about Hive, and in general, the takeaway from all of this is that, again, going back to the merge on read versus copy on write, because this will come up very often in the context of Hive, of Iceberg. How do you avoid read amplification? How do you avoid write amplification? So these are some best practices that you can adopt around that. And the question of compaction always comes up, right? So what do you do? How do you improve your compaction speed and performance, overall performance? So at least in Cloudera, we have done some work around work with Spark. So Spark allows procedures to do the compaction. There is also Airflow in that you can configure for doing compaction of your delta files. So yeah, I mean, there are multiple ways of going about it, but the key point is that if you want to improve performance, there is not a lot of other options besides doing more compactions. Okay, any questions on this part? Otherwise, I'll hand it over to Bill for doing a demo.
We'll do a mini QA maybe right after this.
Yeah.
Switch it up. Let's connect. There. Then I'm going to share my screen. Okay, so as Alma mentioned that we have, so I'm going to demonstrate some of the Hive Iceberg integration and showcase the materialized view. So what I'm going to do is actually showcase some of the Impala Iceberg. Specifically, there are two features that I think a lot of folks are interested in. One is the in-place partition evolution, meaning that there's a huge advantage of doing in-place partition evolution. Think about your table is a petabyte size, right? So you really don't have to regenerate your entire table when you change your partition spec, right? So this is something that we're seeing tons of customers are very interested in this feature. And the second one that the one I want to try to do is the time travel. Time travel just refreshes that you can always go back point in time to reproduce the query results. So this is the time travel feature. So the data sets that I'm going to use is the airline data sets. So this is a public data sets that we downloaded just to showcase some of the Iceberg capability. So just want to let you know that the data size is actually, it's pretty big. And so let me, I just run the query now. Hopefully the virtual machine is still up and okay. So this is good. So want to share with you that this is the data sets that we have, right? So the data sets is essentially from 1995 and all the way to 2007. And we did a couple updates to this data sets to produce some of the snapshots, because every time we do updates to the data sets, their snapshot will be automatically generated. Why do we want to do that? Actually, we want to demonstrate some of the time travel capability. So first thing first is that, this is kind of a number rows, right? So as you can see in 2007, 2008, the data, number rows is almost same. So let me share you why we're talking about this. So in order to do the in-place partition evolution, so we have developed the syntax such as alter table. So this is the syntax that you can do. Essentially, before, let's say 2007, the data sets was partitioned by year. And then after 2007, starting 2008, what I like to do is actually partition the data sets by year and month. So this is actually the syntax that you can use. So I already did that, so I don't have to execute it again, but just want to share with you, that's the SQL syntax you can do, essentially change the partition schema. And so what I like to do is actually to describe this flight meetup. So the reason we pick flights is that the flights actually has the largest table size in this public data sets. So let me just do this. And what I want to share with you is some of the properties of this table. Number one is that, as you can see, the partition transformation is already done. So there's a 2 year and a month. So this data set is already actually transformed into year and the dates, month. And also what I wanted to share with you is the 30 library. So this is Hive Iceberg 30. So this is the Iceberg table format. So the next thing want to show you here is, okay, after you perform the partition transformation, the partition evolution, the first thing you're going to see is that the data size that you're scanning actually dramatically reduced. So before, as I mentioned, before 2007, if I would do, let's say, describe table, we're going to share with you is that what kind of data sets that you're actually scanning. So let me do expand query. So in this explain query that we're going to share with you is that if this is the amount of data size that you actually going to scan, right? So this is 145 megabytes. That's actually before the partition evolution. And then let me scan the 2007. Let's see what kind of amount of data that actually is being scanned. So let me do explain queries on that one. So but now remember, it's 145 megabytes before. Now it's only 11 megabytes. The reason we're doing this is, of course, showing you that the less the data scanned, the higher the query performance. So this is one of the advantages we're seeing during the in-place partition evolution is that being aggressively partitioning your table, that you can actually increase your query performance from that perspective. So this is one of the use cases that we're seeing over and over again that customers are very interested in getting the in-place partition evolution. The second thing is that what I like to do is actually to do time travel, right? As I mentioned that I already had some updates to the data sets. Every time you do update to the data sets, there will be a snapshot automatically generated. So within those snapshots, what I can do is actually always going back in time. So let me share with you that here is the data set, the updates that we have. Each snapshot, you have a corresponding timestamp. When did you actually do the snapshot, and then also its corresponding snapshot ID. Why do I want to show that? Is that I can going back a point in time, doing time travel either by timestamp or by snapshot ID. So let me start executing this. Right. So this is essentially the time travel going back in point in time, showing you that what kind of records at that time, essentially is the 2023 May 8th. That's the data sets that I have. So I can always, so snapshot is one way to do it. And the next thing is that, timestamp is one way to do it. And then the next thing that I can do is go back by the snapshot ID. Let me executing that snapshot ID as well. So this is essentially giving the same result sets as it just to kind of demonstrate that you can actually go back point in time either by timestamp or snapshot ID. So this is just a quick demo just to highlighting some two very important features that we're seeing a lot of the users are very interested in. That's the time travel as well as the in-place partition evolution. So we're gonna do a mini Q&A because Aman and I just talked about the Hive and the Impala Iceberg integration. So any questions? Any folks online are interested in asking questions because this is all live. So you can just open up your mic and ask us questions as well. So it's just not limited to the folks in the room. All right. The next topic is that, so we still have a chance to actually do a Q&A after all the session ends. And so next, I'm going to ask Asif to share his work with Spark and the performance improvement that we're doing.
Excuse me. I think there is a question on the chat regarding the Iceberg table format and whether it needs HDFS or not. If someone can answer that.
I took a stab at it, Bill.
I'm Asif Shahid, and I'm working as an engineer. My area of interest are normally Spark, now Iceberg 2. Through this presentation, we want to share the work which we are doing to improve the performance of join queries, namely inner join and left semi-join which satisfy some particular characteristics, namely if they are implemented in terms of broadcast hash join operator of Spark. So this idea basically takes the dynamic partition pruning concept of Spark little further. So before we delve into the work which we are doing, I would just refresh or give a brief idea of what DPP is, which is an existing feature of Apache Spark. That's dynamic partition pruning. By the way, if you have any questions during the session, please feel to interrupt. That's okay. So, as I said, this is an existing feature of Spark. It improves the performance of join queries, irrespective of the nature of join, whether it's sort merge or broadcast hash join. So this is a sample query which shows where DPP can help. It is a simple inner join query where the joining column is state underscore name, and this state underscore name is a partition column on table census data. So, and there is a filter on the right side of the joining table, GDP greater than some number. So such type of queries can be executed efficiently using the DPP. So how the DPP works is, now this is a current tree, the abstract syntax tree of the query, which would be formed. You have a project node on the top, then a join node. On the right side, you have a filter and table. On the left side, you have census data, and the data on the storage format is Iceberg, and the partitioning column is state name. So you can think of conceptually that the data files are being stored per state name. So let's say there are 4 unique state names: Arizona, OR, California, and Colorado. So because of the presence of this filter here, it is expected that it will reduce the result set size coming out of stable state economy when joining. So hypothetically, let's say that because of this GDP filter, which is a non-trivial filter, the number of rows which would come out would have only 2 of the states. That is, say, OR and California. So it would be nice if the left side table could somehow skip scanning the directories Arizona and Colorado, because those will never satisfy the join key. So how does DPP achieve this? So DPP would fire something like a Spark before actually executing the join query, will fire a query similar to like select distinct state from state economy where GDP greater than blah blah, this number. So that results in state name of 2 unique values, OR and CA. Given this information, now Spark can push down an in filter on the census side. As a result, it will be able to, and this filter is a runtime filter. It's pushed at the very fag end of the query execution before the actual join query executes. So because of the presence of this state name in ORCA filter, which is pushed down at the data source V2 level, and those data source V2 level which supports runtime filtering, those interfaces, they are capable of taking this in filter. As a result, it can skip these 2 partitions, Arizona and Colorado. Now, if the join is, so there is a cost, the overhead cost is the DPP query. And if the GDP filter is not selective, if the filter on the right side is not selective enough, in the sense if it's going to scan nearly all the rows, or there is the number of states which would be coming out would be identical to the total number of partitions, then there is no performance gain in any case. It will, in fact, there will be a performance loss. So presence of a non-trivial filter on the right side of the table is a pretty important requirement. One thing to note is that if the right side of the table was a broadcast build side, basically if the join was a broadcast hash join means that the build side of the table, after applying the filters, all the rows are broadcasted to all the executors. So in that sense, if there is a broadcast hash join available, then DPP query is not needed, because the keys broadcasted by the broadcast variable itself is the filter. So in that sense, Spark already avoids firing the DPP query if it's a broadcast history. If we keep this in mind, then this is how the final query plan would look like before execution of the join query. It has pushed down this runtime filter state name in ORCA, which would be able to ensure that Arizona and Colorado folders are not even touched, because the manifest file, the way Iceberg partitions the data, it knows that, okay, it does not have to scan any files in the EZ and CO folder. Now, given that, in summary, the DPP improves the performance of join queries when one of the joining column is partitioning column and a non-trivial filter is available on the other table. It works by reducing the number of partitions to scan for building the join. And if the DPP query is not selective enough, in the sense if it scans all the states, then there is no performance benefit at all, because it's going to scan in any case all the files of all the directories. Now, can this DPP concept be taken further? One thing to note is that right now this DPP query requires the left side table to have a partitioning column, because if the column is not partitioned, then it cannot directly eliminate directories, because first of all, there will be a cost of DPP query to get the data, and then secondly, the pruning might not be effective. In the sense, it will not be able to eliminate all the directories, because it's possible that the partitioning column, the join query was on a non-partitioning column, but it was distributed across all the partitions, the joining keys. So in effect, it has to go to each file. But is there a way where this can be effective even in case of non-partitioning column, and we don't hit the cost of DPP query? That is one requirement. Second is that in case of Iceberg, that's to the best of my knowledge, looking at the code, I'm 90% sure that the runtime filter which is pushed in, since it's on a partitioning column, its usage is only at the driver, because once it has identified that these partitions need not be considered, then that filter as such has no meaning on the executors. It is never sent on the executors, because in any case, the column which it was supposed to prune, that it has already done by selecting the right manifest files, the right folders. Now, but there is a case where the joining column is little different from the partitioning transformation. In such cases, the pushed filter even has a meaning on executors. For example, let's say I am joining on roll number, but I am bucketing on bucket, say taking some modulo of roll number, say in 8 buckets. Now in such cases, further filtering is possible by the runtime filter on the executor itself, because you are just right now eliminating some buckets, but still that bucket might be containing not relevant roll numbers, because the actual joining column is roll number, but bucketing is on a transformation of the joining column. In such cases, that in filter even has a meaning on executor, but that is not being sent. And the reason for not being sent most likely is that the cost of serializing the values in might be pretty high. So can we even utilize in filter in such cases on executor to do further pruning without hitting the cost of serialization? There are max min available on each column in the manifest file that is at the driver level. On the executors, if the data is in Parquet, you have min max on columns, comparable columns at row group level, at chunk level. So there are multiple places where there is a range min max available, and can that be utilized to prune the number of rows which emanate from the iterator on the executor. So given this, if you look at it, the broadcast hash join of Spark actually satisfies all the criteria. Given that the broadcast variable is broadcasted to driver and executor before actually the query executes, the serialization cost of the in query, in filter, the values, that is gone. You just, because it's already available on the executors written on the file, you can deserialize it. So what is required is that instead of in filter, you create something like range in, which is nearly in, but instead of set, you have a sorted set of keys. Sorted set because we want to prune the ranges. The question is that if same range in filter is being serialized to executor, each partition would try to deserialize it from the broadcast ID, because we are not actually serializing the keys, we are serializing the broadcast ID. So the deserialization cost and creating multiple copies, that needs to be avoided. For that, using caching and weak references, we can ensure that in a single VM, only once a deserialization is done. So even if multiple partitions execute in the same VM, they would all be referring to the same instance. And as I said, that since the range and filter which we are creating is not actually storing values, but a sort of a pointer to the values. So the serialization cost is removed. Now, how does this prune? This is a simple example. Let's say the range and value, the broadcast ID variable containing the broadcasted keys, when deserialized and created in a sorted set, has this ascending order of 1, 5, 9, 15, 23. And let's say there is a column X, which is the target of pruning. Its min-max states are available. And let's say it's 10 to 40. Now that min-max state can be either on the driver in terms of the manifest file, or it could be at the executors in terms of row groups and chunk. And there are 2-3 levels where such page store level also. So there are 3 or 4 places where such min-max are available. So you can check that if 10 to 14, the range is 10 and 14, since it's not lying in this set at all, that means you can skip reading this chunk or manifest or row group. Of course, the requirement is that the column should be a comparable type. The changes are needed both on the Spark side as well as Iceberg side. Iceberg side to take in this range and filter, which has a special value, which is not actually the set of numbers or comparable values, but a broadcast variable, reference to the broadcast variable. And on the Spark side, the changes have to do mostly with the AQE related work, which is because AQE aggressively evaluates the build side, and we do not want to evaluate the subplans till we have pushed down the filter on the iterator, because once the iterator is opened, then after that there is no point in pushing down the runtime filter. It's not going to do anything. We have already taken the cost in such cases.
Just a second. Yeah, sure.
Uh,
Yes. It's like
so
with those.
Could you please repeat the question for the online audience?
So the question is that can't we do the filtering at the split levels itself?
I mean, you can do it with Iceberg because get all the without the information to Iceberg. But even in like one of five, it is better it's light.
So there are. I will study more about this, but I have encountered some multiple issues here. It is that the join, whether it's a broadcast hash join, that is decided at the optimizer level, and the splits, especially the iterator, is opened much earlier for deciding whether it's a broadcast or because of the cost, like whether should it be executed shortword join or broadcast hash join, etc. So the iterator and splits have already been calculated. That's the first thing. Second is to get the splits, what splits to prune, you still need the broadcast hash join, the keys. But that happens at the fag end. The plan is executed. So you don't have that information at all at the time of getting the splits. And there are other things, especially in case of AQE, there are more subtleties. In fact, I'm going to even share one issue which our colleague has found, where the reuse was not happening of the exchange of filter, and that has got to do with this runtime filter being pushed. But that aside, so the main thing is that because pruning on the basis of splits require information of those keys, and those are not available till actually the, in fact, it is the broadcast hash join is available when the code gen is happening. When the call comes into the do produce of broadcast hash join, at that point the broadcast variable is actually distributed and broadcasted to all the nodes and even evaluated. So we are already past the split timer. Any other questions? Even online audience, if they want to, please feel free.
So the changes that are required in Spark for this, have they been implemented, in particular in open source version of Spark?
No. Right now, it's very much a work in progress. We are nearly 90% done. In fact, there was a revelation only yesterday, so I need to work some more. But it's too early to say whether there are too many ifs and buts to get into the open source. So it is not there in open source, but it should be available in our releases, hopefully in near future. So my colleague, ex-colleague, Eugene, so this is an example query again on the lines of the previous one, where the work which we are doing actually comes into picture. So everything remaining same, the way the runtime filter has been pushed, the only difference being that here it is a join on the course ID, and the non-trivial filter is this courses instruct length. And now we are actually pushing down this range and filter, which I am calling, on the students table. And note that the joining column is not a partitioned column. So let's say that the keys of interest are 3, 7, 11, 18, 25. Now, in Iceberg, you have the manifest file, where the manifest file contains for each path which this manifest file governs, and we estimate the driver, a lower bound and upper bound of each column. So, given that the range is 3, 7, 11, 18, 25, these are the keys of interest. And the lower bound and upper bound of path 1 is 1 to 3, 4 to 6, blah, blah. So the green are the paths which should be included. The whites are the paths which should be excluded. So using this navigable set range and this simple logic, like we can see whether it's able to prune or not. So range dot ceiling lower bound. This will give the greatest or equal to number which is the greatest number which is greater than or equal to the lower bound. Now in this case the lower bound is 1. So the greatest number which is the least number which is greater than the lower bound will be 3. Now if we compare 3 compared to lower bound, is 3 equal to 1? No. So we come down here. Is least number greater than or equal to lower bound, which is 3? 3 when compared to upper bound, is it greater than 0? Upper bound is 3. It is equal to 0. So it will go into the else, which is it will keep it. If you consider the second path, 4, what is the number which is the least element greater than or equal to lower bound? In case of 4, it is 7. Now, if it is 7, we come and else. Is 7 equal to lower bound? No, lower bound is 4, so it's not. So we come here. Is 7 when compared to upper bound, is it greater than 0? Yes, 7 is greater than 6 because upper bound is 6. Hence, this path is discarded. So, by this logic, you can prune the data set to be scanned at multiple places. Manifest file is at the driver, but as we go on the executors, you have such min-max available, as I said, at row groups, at page, at chunk. So, you can keep on filtering. What are the possible remaining work and other possible future enhancements? This is something which dawned on us only yesterday while working with my colleague. We were still not seeing the performance benefit which we should have seen. And the reason it turns out is that the range set is the actual valid keys which are of interest. So once you have pruned the groups, when it comes to the point of individual row, you can always check on that individual rows column value whether it actually satisfies or not. As a result, you can decide even like just at the data source V2 level itself, before the row emanates up, whether to prune or not. Like we have in TPC-DS a query 16 where the base data source, base table has, in case if the factor of generation is 0.3, around 5 million. And there are 3 joins nested. I can see that at the third join, the total number of rows which are coming out is just 3,000. So ideally, if I have pushed all the keys down, then only 3,000 rows should have actually gone up from the data source table. But I was seeing around 580,000. So the reason is that because by default the read mode is vectorized, what is coming out from the Iceberg iterator is a column batch. So you are never actually dealing with the individual row at that level. It has already reached in the domain of Spark, where the individual rows are like individual variable, the elements in the code generated are taking the value. So our filter was actually at the iceberg level, but it couldn't actually filter out individual row. As a result, we didn't see that benefit. So we have to ensure that what filter which has been pushed down at the iceberg level also gets applied in the code generated part of Spark just after it has deserialized the column batch and is dealing with individual row. So this is that red thing which you have to take care. The other work which can happen in future is that it is a multiple column compound join, basically A equal to X and B equal to Y. Spark will push only one of the filters down. We do push two range in filters, one for A and one for B. But here what happens is the pairing information is lost. For a particular value of A, there exists only one value of B, particular value of B, which is a valid combination. But because you have instead of horizontal pairs, you have a vertical split. So as a result, if you look at this structure, the range in values for A are 1 and 2, for B is also 1 and 2. As a result, these 4 paths will be selected. Ideally, it should have pruned these two, A equal to 1, B equal to 2, and A equal to 2 and B equal to 1. They should not have been selected. But right now, what will happen is it will select all the 4. So some work can be done to do more effective pruning. The other was this colleague with whom I'm working, Rajesh. He has found that in AQE, the reuse of exchange of subplans is broken. Reuse does not happen. And the cause is that the current DPP runtime filter, which is being pushed by the DPP, it breaks the equality and hash code of the batch scan exec. So what happens, we will be filing a ticket and proposing a fix also soon. What happens is that in AQE, there is a stage where the one plan, one leg, has the DPP filter pushed down to the underlying scan. But the other side, where we are comparing this branch with the other, the filter is still remaining at the batch scan exec level. It has not gone down to the actual scan. As a result, the equalities break, and so reuse does not happen. The other is this new suggestion, again from Rajesh, that if we can utilize the sort merge join blue filters to do the data source level pruning of the data files being scanned. That is also one of the things. Now, these are I wanted to actually get much correct numbers, but as I said, that since our filter was not executing on the row level, I was not seeing that improvement. Here you focus on the blue and the orange. So these are some representative queries. Like I am enthused by this blue and this query 95. This query 16 is where I'm only seeing a delta, but it has the potential to go down to, say, somewhere here. Because the number of rows which should come out from the base level should not have been more than 3000 in that test. So in a couple of days, we'll get more solid numbers. So that's it from my side. Any questions or queries? Thanks.
So we're going to take a short break. Pizza just arrived, so please grab pizza, and then we have some drinks here as well. So about like 15 minutes, and then the next one is actually a couple of speakers from LinkedIn. They're going to talk about their Iceberg innovations. All right, let's resume the session. So that's what. So before the session starts, what we like to do is actually, I know that some of the folks are using Iceberg at their firm, And anyone would like to share their Iceberg experience, how they're using Iceberg today, and what was most interesting things that you guys are interested in from here, this meetup? Anyone? How about Rohini? Are you able to share some of your Iceberg experience with us?
As part of the cloud migration. Probably he's a better candidate.
So we are like just starting to use it. Like so far we haven't like migrated any data set. So we are like just building the ecosystem that's necessary for people to start using like within Yahoo to migrate their data to Iceberg. Like we recently like last year we announced like we are going to migrate all our data to cloud to AWS and GCP. So while doing the migration, we are planning to migrate the data set to Iceberg to cut all the cloud related cost that happens. So we don't have like use case or like real production jobs that's running so far. So there are like some gaps that we are trying to fill out. That's the main reason we came here, to figure out like things like how everyone else does those things in production. Like for instance, the OZ support, those sort of things, to detect if a partition exists or not. So those kind of use cases, we just wanted to check like how everyone else is doing. So that's one reason why we came here mainly.
Yeah. Thank you for sharing this. Anyone else? All right. Why don't we have I see Wala already ready for the next session. So next one is LinkedIn folks are going to share their experience with Iceberg and their innovations.
Hi, everyone. I'm Wala Mustafa. I'm joined today with my colleague Asta Agarwal to talk about incremental view maintenance with Coral, DBT, and Iceberg. Okay, so in modern data lake architectures, it is typical for users to use a number of query compute engines such as Spark, Trino, and Flink to process large amounts of data. And at the same time, they use orchestrators such as Airflow to manage the execution of their jobs on top of those engines, which typically happens on a schedule or based on data availability. At the same time, they use ETL tools such as DBT or Jupyter notebooks to help with implementing, testing, and building their data workflows. And at the center of all that, there are a set of tables in the data lake, which are continuously updated with data that's either coming from the application side data sources or from other tables within the data lake itself. However, with the access to a large suite of data productivity tools comes the other phase of growth pains of data lakes. So users or developers tend to implement and deploy a large number of jobs, typically in the form of SQL workflows, which end up scanning and computing data from scratch each time they run. And this becomes more of an issue as the data grows larger in volume. Okay, I think there's a missing slide, but we're gonna get over that. So to avoid the pains of having to recompute the data every time from scratch, we propose a set of using a set of tools to automatically compute data incrementally. And incremental computation doesn't only save compute cost, but also helps with improving the user experience, where the user doesn't have to think about the mechanics of the query, incremental query plans, but also focus on the business logic and be able to build entire workflows by just listing a number of SQL queries. And to achieve that, we leverage a set of tools that are powerful for the data productivity ecosystem, such as DBT, Coral, and Iceberg. So we use DBT for capturing the transformations from the end user, and Coral for logic rewrite and for inferring the incremental version of the user query. And we leverage Iceberg for its time travel capabilities and snapshot and incremental scan APIs. So let's start by the first tool, which provides the user-facing experience, which is DBT. So DBT stands for Data Build Tool, and it's an open source data transformation framework that enables users just to focus on the transformation, and then it helps them with executing that transformation as a job on top of multiple execution engines that are pluggable. So users can plug and play different kinds of engines while maintaining the same user experience and the same way to express the logic. So as a concrete example of how user experience goes while using DBT, DBT exposes a concept that is called a materialization. And that concept allows the user to tell DBT how to deal with the query that the user specifies as the core of the job execution. So in this example, the user specifies the select statement, and upon execution with the materialization that is called table, the DBT engine would execute that query fully and have its results materialized to an output table. And upon the next execution of the DBT job, the query would be again re-executed and the output table would be dropped and replaced with the new version of that table. There is also another mode of execution in DBT based on a materialization that's called incremental. And in that mode, the user adds annotations to the query, typically in the form of where statements or where clauses. And those where clauses indicate to DBT what are the additional portions of the query to be evaluated upon further executions of the query so that they can be reflected on the output table. But as you can see, they require additional annotations and additional logic in the user and additional work from the user to be done. And they are actually designated in the DBT documentation as for advanced usage. So what would the ideal experience be is to have the user still express the query in the regular batch form without having to think about those additional annotation, but also have the system in the background figure out how to execute and implement that incrementally. So to understand how that works, let's take a quick overview of incremental view maintenance techniques. And through that example, where we're joining two tables, one that is the inventory table and the other is the prices table based on the ID. Let's say that at time T1, these are the versions of the tables. And at T1, the join results would have the tuple based on the ID 2 shown in the output. At T2, the tables would receive more data, and to recompute the results, that version of the table would be dropped, and then the join would be recomputed. The join would be fully recomputed again to have the output table replace the older version of the table, and that would become the output at T2. Let's now go through the same example in incremental mode. So in incremental mode, again, we start with the T1 version where the initial state of the table produces the initial state of the output table, which is T1 in this case. But then when updates happen to the underlying tables in the form of green color here or green rows, we start adding rows to the output table incrementally. In this case, to produce the incremental result, we take the incremental update to the right table and join it with the existing data from the left table. And that is denoted by delta T alpha in the slide. Similarly, we take the updates to the left table and join it with the existing data in the right table. And that is denoted by delta T beta in the slides. It happens to be empty in this case. And finally, we combine or join the results from the two updates to both sides of the tables by joining the two green colored rows to produce delta T gamma. And all of these together constitute the output that needs to be appended to the final table. So the query that we see on the slide right now is the incremental version of the query that we've shown at the beginning. So what we ideally want to have is to have the user express the non-incremental version of the query, but have the execution engine execute the incremental version instead, do that type of rewrite. So to see how we connect all these tools, dbt, Coral, and Iceberg, to produce that type of rewrite, I'll hand it over to my colleague Asta to talk about Coral and the rewrite aspect of the query. Over to you.
Thank you, Wala. So let's talk about Coral now. Coral is an open source framework for SQL translation, analysis, and rewrite. So Coral enables interoperability of the same SQL query across multiple execution engines by enabling conversion of a source SQL, by enabling conversion of a SQL from one source dialect to a target dialect. It can also help with query rewrite and analysis, especially to support emerging use cases around data governance. So if we want to obfuscate certain data from being projected to the end user, we can write some transformation rules in the query plan level to preserve and hold back certain information. Coral is an open source since 2020, and let's see how it enables all these features. At the center of Coral, we have a standardized representation called Coral IR, which is an engine-agnostic representation. We provide adapters to convert any input representation into this Coral IR and back from this Coral IR to any output representation. The Coral IR is based off of Apache Calcite's representations, and it has two semantically equivalent representations. The first one we call the Coral IR, which is the abstract syntax tree. So it preserves the query semantics at the syntax tree level, and it extends this Calcite SQL node representation. This Coral IR helps primarily with SQL translations when we are looking to convert a SQL definition from one source dialect to a target dialect. The other semantically equivalent Coral IR is based off of Calcite's red node representation or the logical plan representation, and it can be utilized more effectively in query optimization or rewrite use cases. Let's look more closely at the AST representation. On the left-hand side, we have two equivalent SQLs written in two different dialects. They're both trying to join on tables foo and bar with an additional where clause. And as you can see, in the where clause has a condition on B, on the first element of B, and the semantics of selecting an element from an array are different across Spark and Trino. Spark has zero-based index arrays, and hence we have a B of 0 representation on the Spark SQL. But the same thing can be represented in Trino by using the element add operator, and the array is also one-based array instead of a zero-based array. The other difference that we can see is the difference in the operator in string in Spark and the string position operator in Trino SQL. Both want to achieve the same result, but they're represented differently in the two dialects. However, Coral allows to represent both of these SQLs in the standardized Coral IR AST representation on the right-hand side, where the operators are represented in a standardized representation, and they can be converted to and from either of these SQL-specific dialects. The image has also been generated by another component of Coral called Coral Visualization. Now let's look at the other IR representation, which is based on Calcite's logical plan. Now we're looking at the same SQL again, however, in a logical plan form, where we're projecting the queries, and the child node is a filter-based node, followed by a join on the two queries. These two IRs are interconvertible, and they both are equivalent and can be converted to any of the input or the output representations. So let's look at how it ties back to our original problem statement. We've just established that Coral can help us convert between any input and output representation. And from the purpose of incremental view, we are looking to convert our input SQL definition into an incremental SQL definition. So going back to our join example between the inventory and the prices table, let's see how we can generate the incremental SQL definition. Coral incremental is the component of Coral which can take in a SQL dialect specific definition and convert it into, using the existing adapters, convert it into the Coral IR logical plan, which is represented on the right hand side. And Coral incremental module will help us rewrite this logical plan where we are projecting the same fields, but when it encounters a join, it will split that into a union of 3 subqueries, where each join is between the base table, the existing table, and the delta table, or the 2 delta tables as shown on the right-hand side. And the joins are based on scanning data from each of these representations. Using the existing adapters, we can convert this IR representation into any supported output dialect, which would give us the SQL definition. This is it.
Indians tweak. Sorry. Question is that does it only give output as a string, or it actually can give a parse tree in the target SQL?
Both are supported outputs from Coral's perspective. We can also return the plan, and we can also return it in the string form in the SQL text definition.
That would say.
Another component I want to highlight is Coral Service. Coral Service is a standalone Spring Boot service where we expose REST APIs to enable these translations or any kind of optimizations. The specific endpoint for incremental rewrite is the endpoint that accepts this input SQL and returns you the differential incremental SQL representation. So as an example, you can interact with this tool using a simple UI, or you can also send a curl on your terminal. We send as an input the query that we want to translate. And as an output, we receive this transformed SQL, which is the incremental representation. So we set out to set up a framework where we would be able to do efficient updates to our base, to our materialized view or our base tables. And the other important aspect to this framework is low friction adoption. We're looking for a framework which can be easily integrated with the existing tools and can be plugged in easily, and will also enable efficient updates instead of entire recomputation. So let's look at how all of this ties back with DBT. As Vala already mentioned, DBT is an existing framework where if you set it up in the table mode, it will, every time you execute your DBT the script, it will recompute the SQL from scratch, dropping the previous snapshot. And what we are looking to do is set up a materialization mode, a different materialization mode, which would enable efficient updates. And that is where Coral DBT comes in. Coral DBT is another component of Coral, which will set up a materialization mode where if given an input DBT script, it will generate the most optimal plan, rewrite plan, and then it will also generate the Spark Scala code around it so that your engine adapter can execute that entire script and update your materialized view. So we've already looked at how we can use Coral service to generate the incremental SQL. So let's now look at what is the Spark Scala code needed to wrap this around. We've been talking about two sets of data sets. One is the data which already existed in your base table, and one is the delta data that has been added to your table. So how do we actually set this up? For this, we turn to Iceberg table property snapshots, which has snapshots of data added to the table over time. The snapshots allow us to time travel and write queries so that we can query data in a specific time window. So we can grab the snapshot ID from our last dbt execution run or any other metadata to realize the data that has already been processed. And then we can grab the latest snapshot ID, which suggests what is the most recent data that has been appended. By using Spark Scala, we can query data up till the previous snapshot, and we can query the data between the previous snapshot and the most recent snapshot to generate the delta data. So, tying this back to our existing example, we will query the data up till the previous execution and store that in inventory. And we will make another inventory delta, which will query the data between the previous run and the most recent snapshot ID. Else Coral service will return you the incremental SQL, which has been returned in terms of the base tables and the delta tables. You can compute that response and append it to your original output table. So going below in the diagram, at the previous snapshot, we had at T1, one record added to this table. And at T2, when we append the query response, we've appended the two delta records to this table instead of dropping and recomputing things from scratch. And that's how we've achieved both of our objectives, which is an efficient update enabled by a low friction adoption by integrating this framework into an existing tool, dbt. As for the next steps, we want to support more complex queries, which have aggregates, nested joins, aggregate over joins. And the use case I just presented has more to do with append-only tables, and we want to extend our support for use cases if the base tables also have updates or any kind of deletes. We also want to identify how to build a cost-based model so that we can identify the most optimal plan for a given SQL definition. So that may involve not materializing any of the incremental tables, or that may generate multiple plans, and we may need to weigh in on which plan is the more optimal plan. I've linked some of the references to our Coral project and the sub-repositories where we have the code base for generating this incremental SQL and also for the dbt materialization mode that you can check it out. And I want to call out the contributors for this project who've worked on this in the past several months. That's all for the presentation. Thank you.
Thank you very much. And I'm going to open the floor for Q&A. Folks, you're online. You can also ask your questions through the Zoom, LinkedIn as well. So any questions?
Clarify the question which was asked previously by Rohini about the splits. So on further thought, yes, the splits are recalculated, and the number of splits may reduce or may still be same, but still the runtime filters need to be passed to the executors, because even if the split is selected, that does not mean that all the values would be within the range. So there can be further trimming happening. So the way Iceberg opens the manifest files, and in a single split, it might be reading multiple manifest files. So it is possible that one or two manifest files might get removed. So the number of splits might not change, but the amount of files it might be reading would be less.
Any other questions from the audience? Yes.
Hey, I'm David. Yeah, I have a question about whether you've thought about, can you identify queries that could be improved by adding like a partition column? Because you're analyzing these queries that are supposed to be kind of incremental, but there are like partitioning strategies that could help you make it even more efficient than potentially it is today. Does that make sense? It's basically, yeah.
Yeah, so I guess this might be like an independent application of incremental rewrite, but definitely if you have a tool that allows you to parse queries and understand them, then you can go through your logs and understand your query workload and then figure out which queries would benefit from what types of partitioning.
Yeah, exactly.
String techniques and so on. So that's definitely something we're looking forward to. But yeah, I wouldn't have the bandwidth to do it yet. But.
Are there any other, I don't know, kind of suggested optimizations that you've thought of? Because yeah, it's kind of interesting. You have these people who are trying to make these incremental updates and you have the entire query plan. So it feels like, yeah, there might be even more opportunities to suggest improvements.
Yeah, there's a lot of improvements that could be done with having the insight. So one other improvement could be to understand your data more or understand your schemas and maybe annotations. So some of the applications also include, if you have sensitive data and then you have workloads on top of them, how do you identify that the output is also sensitive? That's one application, definitely. Another is materialized view substitution. So you could have query workloads and then you can figure out, okay, that subtree I have seen before, I might have cached it or I have it as a form of a table, then I could just substitute it with an existing table.
Yeah, that makes sense.
Lots of applications, we can talk about them offline as well.
Awesome. Great. Thank you.
All right. Any other questions from audience or any questions from Zoom?
Just to add to what Vala was mentioning, another optimization we could do also, we could skip even rebuilding the materialized view on incremental maintenance if it can detect that the data change does not affect the MV or the materialized view, and the predicates used in the query to produce the materialized view is not affected by the data change. And you can actually completely even skip regenerating or rebuilding and maintaining the MV. So only maintain the MV when your data changes affect the materialized view results.
Thank you. Any questions?
I have one for a little bit earlier when you're talking about the time travel. Were you having to specify a specific time interval, or were you kind of doing more of a, I guess, can you explain that a little bit more?
Oh, yeah. So you're talking about the demo I did on the time travel, right? So actually, nobody will remember the exact timestamp, right? So what we're doing is actually all you need to remember is some approximate time. So let's say 2 p.m. last Friday. That's all you need to actually put in the query is the 2 p.m. last Friday. And then what the time travel will do is actually find the snapshot actually closer to the time that you have specified. So this is how we're implementing this time travel. Does that answer your question?
It does. Can I ask a follow-on too?
Yeah, sure, absolutely.
Yeah, can you go into a little more detail on partition evolution and what happens when you actually run that altered table statement? Does it modify the data that's already in the table?
Oh, that's another fantastic question. So when you do partition evolution, so actually we didn't go into the detail in terms of what's very unique about Iceberg is something about split planning, right? So each partition schema, of course, will generate its own query plan. And within Iceberg, when you're executing SQL, you will consider all the split plans that are being generated based on the partition schema. So this is very unique from Iceberg perspective, which is split planning. Now, is that you don't have to, let's say you change the partition schema January 1st this year, and then all the previous data doesn't have to be regenerated, but all the ingestion that are coming after January 1st will be based on the new partition schema. So this is one way that you are saying that we don't have to regenerate the entire table when you change your partition schema. Aman, do you have anything to add? All right. Hopefully that helped your question.
Yep.
Yep. All right. Any other questions, either online or in person? Oh, yes.
Hi, I'm Riza from Cloudera. So, interesting approach there about identifying the delta. Have you ever contrast the approach with, let's say, like just embedding the timestamp column in the table itself to identify the delta? And
Presentation?
yeah, for your presentations.
So timestamp is not necessarily a column in the table. It could be the case that it is, but we rely on Iceberg's metadata, and that's the snapshot timestamp that showed up on the slide. So when we query by a snapshot range, so again, as Bill mentioned, you start from a timestamp, map that to a snapshot ID, and then scan based on those two snapshots ID. Alternatively, the query that was shown on DBT slide in incremental mode, like native incremental mode in DBT, that used an incremental, a timestamp column in the table itself. That doesn't necessarily apply to all tables, but what's nice about using Iceberg in this case is that you get that snapshot timestamp for pretty much every table.
Yeah, I just wanted to add that because the materialized view would be querying multiple tables, right? So you want to have a snapshot for all those tables for for the time that the MV was created. So yeah, if you, let's say, if you didn't have snapshots, then you would use some type of transaction ID or some notion of that to get that delta. Yeah.
All right. Oh, one more question.
So have you seen any changes in and comparison between compute times for without the incremental maintenance and the regular incremental? Like, have you had metrics discovered from them and compared them?
We don't have extensive metrics, but throughout the examples we prototype with, yes, there's observable difference in runtime.
Right. Any other questions from audience? Any other questions from Zoom? All right. Thank you everyone for coming. So let's wrap the session. Thank you.